we're pleased to have Duncan Pettengill from Wolfram to give us a series of 3 lectures. And also there'll be a project attached to this course, and I'll let him describe it. Go ahead, Duncan.
All right. So this course is going to be covering 2 major topics. The first of which is graph theory in the Wolfram language, and the second of which is visualization of functions, data as signals, and other things that you might want to visualize. As the project, basically what we're just going to be doing is taking a number of explorations or problems that are associated with this course. And I think that if the groups were to present 3 or 4 of the solutions to some of the problems, I think that would constitute a sufficiently broad project that it could be presented. But and if it's not enough time, we can cut down on the number of problems and present 2 problems per group. We'll see how it goes, but it's something that everybody in this course will be working on, and then we can present a wide variety of solutions at the end, because that's one of the things that's beautiful about the Wolfram language, is that it admits a very wide array of solutions to different kinds of problems. All right, and let me know when we should get started.
Yes, go ahead and launch in.
All right. So just to double check, is my screen visible to everybody else? All right. Okay, so my name is Duncan Pettengill. I am a technology engineer at Wolfram Research, which means that I do technical support. I also do some consulting, working with people who want to use the Wolfram language to work on various projects. Some people do simulations, some people do modeling, some people just do analysis of data or analysis of, some people just use it for art. I've worked a number of times with one person who exclusively uses the visualization features of the Wolfram language to create his art. It's a very flexible language. And I understand that some of the people in this course have not worked substantially with the Wolfram language before. And so I thought it would be worthwhile to give sort of a very basic Wolfram Language 101. So first, for context, the Wolfram language is the language itself in the same way that Python or C is a language, and the program Mathematica is an interface to the Wolfram language. It is a way of interacting with the language in sort of the same way that that Jupyter notebooks are a way for interacting with Julia or Python, or in a looser sense that Visual Studio is a way for interacting with whatever programming language you're using Visual Studio for. The genesis of the Wolfram language was as an automated replacement for integral tables. It's a language in which the structure of expressions is important. And there are a wide variety of functions that modify structure or act on the structure of an expression. So just some style notes. In the Wolfram language, all built-in functions start with uppercase letters. And anything that is a known function will be displayed as black. Something that is not known to the Wolfram language will be displayed as light blue. And in the same way that you can take the sign of a number, you can just evaluate something like that, the sign of a floating point number. You use square brackets for functions, and then you evaluate it with Shift and Enter. So hold down Shift, then press Enter, and then whatever input you give, you get the output. Now, the Wolfram language is broadly focused on symbolics. As I said before, it's designed sort of as a replacement for integral. It was originally designed as a replacement for integral tables, though it is certainly expanded beyond that now. Something that has a certain form will be returned unevaluated, even if it doesn't simplify to something else. it still is worthwhile to keep it by itself. It won't say, oh, there's a type error or something like that if sine of 2 is not known, because this function is not known. It'll just be kept as itself. It'll be kept unevaluated. And so you can see that the structure of this expression is a symbol which has an argument in it. So it is a head and then a series of elements. And basically every expression in the Wolfram language can be broken down like this. So if I have arctan of x comma y, the two argument format of the arctangent, where it takes the quadrant of the 2D plane that you're in into account. This is an expression that has a head, a first element, and then a second element. And then in general, every expression in the Wolfram language is going to be something like this. And this basically defines everything. And if something has a rule, if a function has a rule associated with it for what you can replace this expression with, it will do so. If I have sine of a floating point number, then the Wolfram language has a rule that explains I can replace this sine of a floating point number with another floating point number that is computed in a particular way. Similarly, if I have sine of pi, that is something that is known exactly. Sine of pi is something that the Wolfram language has a rule for. It knows that it can replace it with an exact zero. Just a couple other little things. You will observe that this is a floating point number with a decimal. This is an exact number. There is no decimal point here. This is an exact expression. The Wolfram language supports exact arithmetic. So 2 plus 2 is 4 exactly. It's not 3.99 with some floating point error. It is exactly 4. It is treated exactly and symbolically. You also have floating point numbers, which are indicated by the presence of a decimal point. And so this, if you expand it out, you will actually see that this is 3.99, etc., because it's not. Some numbers aren't exactly representable in floating point representation. And there are also arbitrary precision numbers where you can assign a precision to a number that is not necessarily equal to the machine precision of your operating system. So if the general expression is like this, then ultimately, if you break each of these elements down into something else, you will arrive at so-called atomic expressions. The atomic expressions of the Wolfram language are the basic core types that can't be broken down into something else. 0 is atomic. It is an exact integer. It can't be broken down into anything else. You can't take anything out of it. You can't get a part out of it. A floating point number is just an IEEE compliant representation of this number. This is not an atomic expression. Sine of 2, where let me just replace that with f of 2 just to make it clearly a generic function that we don't already know. F of 2 is not atomic because it has a head and then it has an element. So I can break it down then into these further parts. I can say that the head of the expression is f, which is a symbol, and I can say that the first element is 2, which is an integer. And so the symbols are the other sort of essential piece of the atomic structures in the Wolfram language. We have symbols, we have integers, we have floating points, and we also have things like complexes are also atomic, rationals are their own separate kind of atomic. And the atomic expression that we're going to be dealing with today is graphs. For efficiency's sake, graphs are kind of their own atomic thing. They are an efficient storage container for graph information. And yeah, so they can't be broken down into component parts. They are efficiently stored as unbreakable objects. So, all right. So that's just a very, very fast crash course in Wolfram Language 101. And now we're going to be moving on to the graphs material. This lecture was originally written for the Data Science Bootcamp, which informs how some of the content of the course was selected. And so this is basically what we're going to be talking about today. We're going to be talking about, getting started with graphs and networks in the Wolfram language, how we actually represent graphs in the Wolfram language, how we construct them. And then we're going to be talking about various ways of visualizing or representing information using graphs in the Wolfram language. And then we're going to be talking about graph analysis, things like measures of graph centrality or cliques or other properties of graphs that might be interesting depending on the application. And we're going to be discussing some of those applications as well. All right. So just talking, about the introductory material regarding the Wolfram language and Mathematica, and sort of what we're going to be talking about today. Do we have any questions just to start with?
There aren't any questions in the chat yet, and so far no one's raised their hand.
Okay. All right. Well, at any time, feel free to put something in the chat, and I will make sure to take a break every once in a while and come and address any questions that might pop up. All right. Well, with that in mind, let's get started. So this course highlights, not only the usefulness of graphs in the Wolfram language, but also sort of the applications historically that graph theory has been used for. Those of you who have more of a math background may be familiar with Leonhard Euler's bridges of Königsberg problem, which is it possible to take a certain route through the city of Königsberg, crossing 7 bridges exactly one time with a particular layout? And basically Euler conceptualized this as saying, imagine there's a park bench at each of the ends of these bridges. And so how can you traverse these benches going from one vertex essentially to another and passing only each edge exactly one time? And then, of course, those of you who are familiar with, electrical circuitry will know Kirchhoff's laws regarding the resistance and voltage and current passing through electrical circuits made out of certain components. Again, something where you can use graph theory to analyze the structure of a circuit. You can use it for epidemiology. You can talk about networks and how many connections you need to be able to ensure reliable communication. Talking about the design of the internet or ARPANET back in the day, ensuring that you can have communication between strategically important locations while having the possibility that any one of the nodes in your graph could drop out at any time. And there's some sort of pure math material going on with random graphs. This is where graph theory starts to intersect with Ramsey theory, talking about how large patterns can be before you have a reliable pattern. And of course, in the modern world, we have so much data with social media and internet networks that that is valuable as well. So these are all things that we have tools in the Wolfram language to work with. These are the kinds of applications that informed the design of the Wolfram language and the graphs framework. So this is just a little visualization of the graphs team and highlighting basically what we can do. So we have information about relationships between employees in our company, and we can represent that information as a graph with nodes and vertices, which may be directed or undirected. And then we have analysis. So we can take a graph, which may come from some data source, and we can perform analysis on it. And precisely what kinds of analysis we're going to perform, we'll get into as we go. So in the same way that points and lines and angles are the atomic elements of Euclidean geometric theory, points and edges are the building blocks of graphs. So basically we have a list of vertices here, and we have a list of edges that connect vertices. In the base Wolfram language, you can only have relationships between two vertices, which make an edge. There are actually extensions to the Wolfram language that you can download from the online function repository, where you can start considering things like hypergraphs, where you can not only have edges that connect two vertices, but also sort of hyper edges that connect more than two vertices. So like a triangle between three vertices or something like that. And so a graph as an abstract mathematical concept is a model of a network. So basically everything is, this is, analogous to how the real numbers are a purely abstract mathematical thing, but they are a very good representation of things like distance. So a physical, actual, real world thing is well modeled by a mathematical abstraction. And so we treat that abstraction as useful. And here we just have a list of various things that we use graph theory for, and sort of how the language of graph theory differs between them. So we have nodes and links, or vertices and edges. They're all the same thing. And when we start having these concepts, we can start talking about interactions. So, I believe all of you are working in physics, so you've probably encountered the Ising model at some point, which is assuming that every vertex, every spin element in a particular magnetic system is interacting with its adjacent neighbors. And so you can start modeling that as a graph. So you have each of these cells, and each of the cells with which your first cell interacts are connected to it via an edge. And then you can start doing things like, if I start taking out edges, or if I start taking out vertices, does the phase transition of the Ising model change? You can start modeling stuff like that using graphs. And of course, in sociology, I mentioned social networks previously. And in biology, again, you can talk about the interactions between adjacent cells, or you can talk about epidemics. Epidemiology is a very graph theory heavy discipline. You should probably be keeping an eye on ideas like contact tracing and measuring how clusters are connected to each other. Less said about that, the better. Moving on to 2021. So, as I mentioned at the start, in the Wolfram language, all built-in functions start with capital letters, and if they are known by the system, they will be displayed with black text. And they are, so graph, the function graph, takes a series of edges, and it constructs a graph from that specification. So the elements that are given to the head graph that are inside the function graph are just a list of edges like this. And you will see that when I evaluate this, when I hit Shift and Enter, it actually returns a graph. It actually returns a visual representation of this expression. So if I turn on vertex labels, you can see that the edges in this graph are exactly those that were specified when I evaluated this thing. So I have an undirected edge between 1 and 3. There we go. An undirected edge between 1 and 3. An edge between 1 and 4, 1 and 4, 1 and 5, 1 and 5, 2 and 3, 2 and 4, 2 and 5. Those are all there. And so you can see that this graph that I have constructed is precisely described by the list of edges specified here. And as an aside, this construction here, where you write a special character by hitting escape and then a series of symbols and then escape again, is pretty common in the Wolfram language for entering special characters. If I do escape P, escape, that gets me pi. If I do escape R, escape, I get rho. Pi is a known symbol, and you can see that it's black, while rho is not, so it's blue. And so you can assign variable name. You can assign expressions to rho as a variable. So I could say rho equals 2 or something like that. And now because it's known, it turns black. At least it should turn black. I think the front end's a little slow today. All right. So I just showed you an example of an undirected graph where all of the edges are undirected. There is just a relationship between u and v, and it doesn't matter whether it's between u and v or v and u. On the other hand, with directed graphs, the order does matter. You get a little arrow pointing from one to the other. And again, let me just turn on the option that displays the vertex names. And there we go. And so we can see 1 to 3, 1 to 4, 1 to 5, etc. So as I mentioned previously, graph expressions are atomic in the Wolfram language. You can't get parts out of them using Wolfram language functions. And hold on a second. Sorry, the Zoom window's in the way. Hide that. So as I mentioned previously, graphs are treated as atoms by the Wolfram language. You cannot break them apart using the ordinary tools of the Wolfram language that you would use to do so. However, you do have functions that are specifically intended to tell you whether or not something is a graph, an undirected graph, or a directed graph. So if I construct a graph here, in fact, let me make sure it's visible as well. I have a set of vertices, 1, 2, and 3, and I have a set of 2 edges passing between them. So I have 1 to 2 and 2 to 3. Is this a graph? Yes, it is. Is this a directed graph? Yes, it is. Is this an undirected graph? No, it is not. And if I take just a very, very simple graph, which can't even really be displayed as a single, it can't be displayed as a graph. There is not enough information here to build a graph, and so it returns unevaluated. Just like if I write, f of 2. I don't know what f is, or I can't do anything with what f is in order to return something from f of 2, and so it just returns unevaluated. So the head of this expression is graph. This 3 equals sign is same q. This means, is the head of this expression literally equal to graph? And in this case, it is. If I go back here and I take the original graph and reevaluate this, this is still a graph. It's still a graph either way. It still has head graph either way. Even though this doesn't display as a nice little graphic, it is still an expression with head graph in the Wolfram language. However, you will see that the graph q function, the function that tells you, is this actually the special atomic thing that has its own container in the Wolfram language, you will see that it is not. Graph of 1, because it doesn't evaluate to something nice like this, because there isn't enough information to build a traditional graph like this, this is not graph q. Graph q returns false on it. And this is just sort of reiterating what I said before, that because graph expressions are atomic, you can't use the ordinary tools of the Wolfram language to get information out of it. So let's say if I have f of 1, 2, 3, and let's say I call this an expression. An expression in the Wolfram language, it returns unevaluated. It's just f of 1, 2, 3. First of expr, the first part is 1. That's the first element in here, and so first returns that. Similar, head of expr is f. I can break down this expression using functions like first head, last, and it'll tell me all of these things that are parts of this expression. But you will see that first on graph doesn't do anything because the graph itself is atomic in the Wolfram language. And it'll tell you that, hey, this expression is atomic, and we were expecting a non-atomic expression, so I don't know what to do here. However, there are dedicated functions built into the Wolfram language specifically for accessing properties of graphs that you might want to know about. So we have a list of vertices, which we don't get using the ordinary tools of the Wolfram language, but rather the dedicated tools that are built into the graphs framework. All right. So beyond literally specifying all of the vertices and edges in a graph, you can construct a graph out of a matrix. So you can use a matrix like this, where every entry is either 0 or 1 to indicate connectivity between vertices. You can use that by itself to construct a graph. So you can see here that 1 connects to 2, 3, and 4, but not itself and not 5. So you will see that in the first row, I have 0, indicating that there is no self loop between 1 and 1. It connects to 2, 3, and 4. So all of those elements of the adjacency matrix are 1. And then it doesn't connect to 5. So that element is again 0. And similarly, 2 connects to 1 and to 5, but not to 3 or 4 or itself. And yeah, so it's an adjacency graph. It's an adjacency graph built from a matrix. And you can also take a graph and use that to make a matrix. So I take the exact same graph and I go the other direction. As an aside, matrix form is a way of displaying matrices in just a nice, clean way. If I take that out, it'll display it as a sparse array, which is in itself a container designed to store matrices where the elements are mostly zeros. You can also just display it as a list of lists. And then matrix form is a container that displays it in a nice, visually pleasing form with those nice bracketed parentheses, so to ensure that you can see that it is a nice matrix, and it has all the properties that we expect for an adjacency graph. Now, even though I've been using this all along, the Wolfram language supports a wide number of options for these functions. So previously, we've mostly been calling graph with just one argument. We've been just calling it with a list of vertices, or a list of vertices and edges. But we can give other arguments as well, and all of these arguments at the end to the function are options that allow us to control various aspects of the way the graph displays. So here I can specify vertex style, which is red. I can specify vertex labels, which have a finite number of options, one of which is name. I have vertex label style. And I have image padding. And so I can give a little bit of a buffer around the edge. But yeah, so if you have any questions about the options available to any of these functions, you can take you can highlight the function name, and then you can see a little bit of a drop-down menu with some basic descriptions of the functionality, or you can search in the help and find selected function in the documentation, which will bring up another window, which will display all of the information you might want to know about the function, including options, various accepted syntax formats, and other properties, and some basic examples as well. Also, my apologies, there's construction going on outside my window, so sorry if any of that comes through. So you can also assign annotations or properties to each individual edge. We've just had the edges themselves so far, but we can sort of tag the edges and assign certain properties to them. So I can see here that it's the exact same kind of graph as before, except I've replaced this one directed edge, 1 to 3, with an annotation of 1 to 3 with a strength of 10. And now I can access this property with the function annotation value. So I can go into this. This is another function that will go into a graph expression and will extract a certain property from it. So I evaluate this. And then I evaluate this, and it gets me back the thing that I put in. The annotation value of the previous expression, this little percent sign indicates the previously evaluated expression in the Wolfram language. The annotation value associated with the previous expression and the edge 1 to 3, the property strength is 10. So we put in an attribute to a particular edge, and we can retrieve that attribute later. All right, so that concludes the introductory section. Are there any questions so far?
Not so far in the chat.
All right. At any time, feel free to ask some questions. Please let me know if there's anything that's not entirely clear. All right. So once again, we are just listing the various ways in which graph theory is useful in a wide variety of fields. We have social networks, we have database design, and in physics we have the classic Ising model and various other sort of cell-based or graph-based systems that are modeled as a large number of small interacting independent vertices or nodes. In ecology and economics, these are all examples of places where graphs get used. And keeping in mind that graph theory is valuable to a wide range of fields, Mathematica is not the only tool that you can use to work with graphs. The Wolfram language also knows about a wide variety of formats. In fact, I believe in the documentation there is a listing of all the formats for everything that Mathematica supports, and these are some of the graph formats. Oh yes, I recently downloaded a documentation-less build, and I think that's probably why this example data is not present. But I will make sure that you all have this notebook at the end, and you can evaluate this yourself on your own machines and see exactly what this is. Unfortunately, I suffered a computer hardware failure, and this is not the computer on which I originally intended to present this. So my apologies if anything technical doesn't quite work. But the point being that even though I do not have the required example data file, the Wolfram language can import a wide variety of third-party formats as graphs. And then you can use the tools of the Wolfram language to work with those graphs. So it is often quite easy to integrate the Wolfram language into your workflow. If you have all these graphs that were constructed in some other programming language or in some other piece of software, chances are very good that the Wolfram language can import it and work with it. So we can also import data from the internet. We can analyze that as well. So this is an example using a social network for Slashdot. And so we can import this from just a URL. I can specify the URL and I can import it from here. And let's take a quick look at what that data looks like. There. So we can see some annotations, some information regarding the the content of this data, and we also have a list of edges. So seeing that the first 5 elements of this, oh, I see. The first 4 elements are not actual edge information. We can take the first 5 parts, or we can take the 5 and onward parts of this list. So basically, we're just going to discard everything that's not actual data, and we can convert all of these to directed edges and display a graph that's built out of them. And this might be large. Actually, it's going to be very large. It's going to be too large to display. But we can get properties such as vertex count and edge count. And this is why I did not want to try and have the Mathematica front end display this graph, because it has 82,000 vertices and 948,000 edges. But you can still work with this data. You can still work with all of the information in this graph. You may not want to try and render it, but you can still use all the analytic tools. We can also do things like import a CSV file. And we can, again, import a piece of data about a particular graph or network as a table, just as a list. And then we can get information about the edges. So we have a source and a target and a weight. And we can include all of these things as elements of an edge in a graph. So we can take a list of edges and a list of weights, and then we can construct a graph which has the edges as the edges and the edge weights as the list we constructed from here. So we have all of these edges, which goes from a source to a target, and we assign each of these a weight as well. And so each of these graph elements has its own individual weight. And so all of that information can be imported from another source and just assigned as, part of the construction of the graph. And similarly, we can, so we've imported, let's see, we've imported from a text file, we've imported from a CSV file, we can import from a TSV file as well. And of course, it may take a little bit of massaging to put the data in the appropriate format, or to trim out some extraneous non-graph related material or metadata, such as these first 4 lines here. But here's an example of importing a TSV file, which is documented as having a particular structure. And in this case, it's the adjacency matrix of the graph. So we can see that each one is a list of 3 numbers. And then we can convert that to a sparse array. As I mentioned before, the adjacency matrix is typically handled as a sparse array because most of the elements of the sparse array are going to be, zeros. And then we construct the adjacency graph. And then we can construct a variety of properties of that graph. So it has this many vertices, it has this many edges, and it's not Eulerian. So there's also a function graph data, which allows you to construct graphs based on, it's certain, named graphs or graphs with certain properties. And so we can see that this is the graph from the start of the lecture. And Mathematica knows about a whole bunch of different graphs. And you can just use these named graphs in the Wolfram language just by using graph data. And in this case, it's also a function that has a dedicated function. It's also a graph that has a dedicated function assigned. Excuse me. You just have Peterson graph, and you get a Peterson graph. And there are also other resources that go beyond the core Wolfram language. There is the Wolfram data repository and also the Wolfram function repository, which extend the built-in knowledge and built-in functionality of the Wolfram language. And you can just call any of the things that is in that repository just from the Wolfram language, and it'll automatically download it and bring it into your current Wolfram language session. Oh. Oh. Everything's gotten very slow all of a sudden. All right, so from the resource data function, we have returned a list of the Florentine families network. So this is actually an interesting example of graph theory. If you're familiar with Renaissance era history in Italy, you may be familiar with the Medici family, a very important and very powerful and influential dynasty in Renaissance era Italy. And if we take this information, oh, no, not doing that yet. Never mind. Okay, so just know that we have this information and that we can look at this graph and see what the connections between these various families might have meant. So we're going to be able to analyze this data later, but for the moment, just know that we can get it. And there are other pieces of data that we can get as well. We can just download all of this information from the Wolfram data repository. So in the meantime, we're going to talk about random graphs. If you deal with thermodynamic systems, as I mentioned previously, you may have a crystal, which has some imperfections. You can model that as a graph, which has some random properties associated with it. A random distribution of imperfections or defects in a crystal is a model for a wide range of things. So, and there are a number of other functions that allow you to construct random graphs or graphs with certain properties. So, saying that we have a uniform graph distribution with a certain number of vertices and edges, we can then construct a random graph which is consistent with those properties. So if I take this, I evaluate it, I get a particular graph with 10 vertices and 20 edges. If I evaluate it again, I get a different graph with 10 vertices and 20 edges. And I can just keep on reevaluating it. As an aside, if you want to get reproducible results, you can use the function seed random. I'm actually going to express the output there. And I will get a particular graph. If I seed random again, setting me back to the same random number generation state, evaluating the random graph again gives me the same random graph as before because it has the same random seed as before. And then we have various random graph distributions that have certain properties. I believe this is average connectivity between vertices is the second parameter. And again, you just reevaluate, generate a wide variety of graphs generate a wide variety of graphs that are consistent with the specified properties. So, and we can specify, graphs that have a certain number of edges in them for given vertices. And so this is useful for saying, okay, well, this person interacted with such and such a number of people, and this person interacted with such and such a number of people. And if we put all of these together, what does the network of potentially infected people look like if we're describing epidemiology? All right. So we've talked about generating graphs. So we've talked about first what graphs are in the Wolfram language. We've talked about how they're represented. We've talked about some of the random constructors that allow us to generate random graphs with certain properties. There are also other graphs that we can use to get there are also other functions we can use to get graphs out of other pieces of data we might have. So for instance, if we have a 3D mesh, which you might generate from an STL or OBJ file, or you might just generate it within the Wolfram language itself. It is a boundary mesh region. So it's defined as a region where we have some boundary, and then everything else inside it is considered to be in that region. The interior isn't constructed out of TETs or anything like that, if you're familiar with 3D modeling. Everything is defined by saying, okay, this is the boundary, and everything that's inside this boundary is part of this region. So we can get various properties like the connectivity between various corners of the edge of the mesh. So we can see that each of these is a set of vertices, a set of edges, and a full mesh of triangles. Though that's a little harder to see. And that just comes from the mesh connectivity of that mesh in 0, 1, or 2 dimensions. So 0-dimensional objects being the vertices, 1-dimensional objects being the edges, and 2-dimensional objects being the faces, essentially the triangles that make up the surface of this mesh. And so if we want, we can just list this as a set of 2D vertices in a 2D plane and capture the same information, just not necessarily in quite as nice a way. So this is a graph 3D, and this is just a 2D ordinary graph. So one other thing that the graph functionality intersects with, as I mentioned previously, there's this whole framework for meshes, working with expressions that are defined by a series of vertices and edges and polygons, and sometimes TETs or tetrahedrons, 3D volumes. So you can take a mesh and you can use graph theory properties to analyze the mesh, and that can be very useful. So if I take this mesh, which is I believe that's a bust of Ludwig van Beethoven, and you can see it has a little hole in it. Let me actually zoom in on that real quick. Yeah, so this is a low poly mesh of Ludwig van Beethoven, and you can see that it's got a hole in the top. So the function mesh connectivity graph will tell us what connects to what. And we can see that if something has a vertex degree of 2, oh, actually, I believe that's at level 2. Anyways, so we will see that these vertices are all adjacent to a hole. They don't have something on the other side that they're connected to. And so by using these properties of the mesh connectivity graph, we can see that there is a hole in the mesh at the place where these vertices are living. So we can see that these are all adjacent to the hole in the, I think there's another hole in the mesh too, somewhere. Yeah, there's one down here. And so we can see that all of these vertices are adjacent to something where there is a hole in the mesh. And we can use the function highlight mesh with these edges that we've already identified, and we can just create a quick highlight of where these holes are. Again, let me zoom in on that a little bit so it's a little clearer what's going on. And so by using a highlight mesh with a particular set of edges, we can see that highlight mesh is using that information that we already computed about where the holes were to highlight the appropriate holes in the mesh. It did what we hoped it would do. It did what we expected it would do. And as an aside, even though I don't believe it's shown here, you can also use there's also a built-in function in the Wolfram language called repair mesh that you can use to identify or to fix holes in meshes. So if I say mesh2 is equal to repair mesh of mesh. Actually, let me be a little more descriptive. You can see that that does not, at first glance, appear to have any holes in it. And when I do the mesh connectivity graph, I have no holes anymore. So again, we can use the properties of the connectivity graph to verify that the mesh repairing function has in fact repaired all the holes in this mesh. There are no more holes in this mesh. There are no more vertices that are, or there are no more edges that are not bounded on, that are bounded on one side but not on the other side. There are no holes in the mesh. All right. So moving on. So there are a wide variety of options for visualization. This might not be the most useful for you. This is an example in biology which talks about sort of food webs. So this gets eaten by this, and this. This gets eaten by this. This gets eaten by this. This gets eaten by this. And so we can display all of these just as the vertices in the graph. You can see here that this has the same purple boundary. This is a graph expression. And we can include information about all of the elements in it as well. And that's part of why this expression being atomic is actually kind of important, because it ensures that we are able to efficiently store all this information and not have to worry about the Wolfram language checking all of these individual parts to make sure they're of the right type. And that's sort of why it's its own separate system. But we can include little annotations. We can include all of these different things for purposes of visualization. And then we can do sort of fancy things like, you know, highlighting the borders around things when we hover over them. It's just getting a little fancy. There's actually a comprehensive tutorial on dynamic expressions in the Wolfram language. So something that, you know, might change when you mouse over it, or something that updates dynamically based on the time or something like that. There is a good tutorial, but it is outside the scope of this presentation. So beyond the basic functions that return graphs or construct graphs, you can also use a number of functions that will allow you to control the layout of graphs. Let's say you have a graph that you want to use to illustrate something, and you want the coordinates of the vertices to be in a particular location. So you have graph layout, graph plot 3D, and a number of other functions that are dedicated to displaying particular kinds of information. So this, I think, is probably going to fail when I evaluate it because I don't have the example data on this computer yet. But you can see that what happens here is we have a graph 3D, and then we can highlight the graph based on certain properties, such as the connected components of a graph. And we can use graph 3D to ensure that it has a particular set of coordinates. And then we can use highlight graph to display these components with a particular color. And there are a bunch of different built-in styles, such as de-highlight hide. These are all listed on the documentation page for highlight graph. So if you want to just hit F1 and go over there, you can see all of the examples and options that they have for this functionality. Similarly, we can take information about a social network, and then we can do things like we can use a particular function designed to plot communities within a graph. So a lot of the time, you want to automatically identify clusters in a graph or cliques in a graph. And the Wolfram language has a number of tools for working with that. And so you can see just based on the connectivity between these nodes, the community graph plot is able to identify and highlight all of these various subgroups in this dolphin social network. As another example, which may be useful to you, you can use visualization about a system and the order in which things are requested and the directions in which various subsystems communicate with each other. I think there's something back there. There. So you can see that you can use the Wolfram language graph framework to describe process flows or something like that. And if you want to use this to describe a system and use it in some other presentation to describe how things are supposed to be working, you can put little annotations in here and ensure that everything is visible, just so everything is clear. So we have just taken a look at a wide variety of ways to construct graphs in the Wolfram language, different pieces, different sources of information. You can import it from the internet. You can import it from various file formats. You can construct it based on certain properties. You can construct it based on historically known kinds of graph. The Wolfram language has knowledge of these. You can also construct graphs based on molecules. The Wolfram language has a built-in chemistry data framework, and you can actually get a molecule's connectivity graph, or you can represent a molecule as a graph, rather. And yeah, all of that's built in. So now we are going to take a look at some analysis of graphs. And we've already explored the very basic things of checking the vertex list and the edge list and sort of very basic constructive properties. Or if we tag an edge or a vertex with an annotation, we've seen how we can retrieve information about the annotation that we put in there. But the Wolfram language also has a wide range of, oh, there we go, vertex count, vertex list, edge list, just these very basic properties. We can already check whether or not something is a directed graph or an undirected graph. And then we can check slightly more complicated things, like is this a loop-free graph? We can check whether two graphs are isomorphic to each other. We can check if it's acyclic or bipartite or any of these other formats, or excuse me, any of these other particular, check if they have these particular properties. Is this graph connected? Is it not connected? Is it cyclic? Is it acyclic? And there are a wide variety of built-in functions. Again, if you go into the documentation, you can see a list of all of the relevant graph theory functions that you can use to analyze graphs. There are also a bunch of classic graph algorithms. Those of you who have studied a little more computer science should be very familiar with properties like finding the shortest path in a graph and talking about the algorithms associated with that. Talking about finding Hamiltonian cycles, finding cycles that pass through every point or along every edge exactly one time. And so we can see this in action. We can construct a basic graph, which we then treat as a maze. And so we can see that this maze was just constructed with a very basic graph, which we gave a particular embedding. It's a grid graph. And then we say that this is a, well, yeah, it's all here. So you can see that basically we have rectangles for the vertices and rectangles for the edges. The rectangles for the edges are I don't know what that is. We can see that they have particular sizes. I'm sorry, there's construction going on outside my apartment. It's very distracting. All right. So we can construct a graph that is made out of particular vertices and edge shapes so that we can display it. And so it looks like a maze. It's very fancy, but it is really just a graph. It has that purple border, just like every other graph we've seen today. And we can find the shortest path through the maze. We have a dedicated built-in function that will find the shortest path. And we can construct a path graph which goes through all of the edges that are returned by find shortest path. In fact, we can take a quick look at what the output of that function looks like. We can see that this is a list of vertices. And so from 1 to 21, from 21 to 22, from 22 to 42. And those are just the lists of the vertices that are in this graph. So 1 to 21, 21 to 22, 22 to 42, etc. And so, yeah, so we can just highlight all of the path that exists in this thing. I don't think that this would have a Hamiltonian cycle in it. So I'm not sure Hamiltonian find Hamiltonian path will do anything. But depending on the graph you have, there may be some useful path or set of edges that you can get using classical graphs algorithms. Actually, hold on just one second. I'm going to take this graph and do basically the same thing. Except instead of find shortest path through this graph, find Hamiltonian cycle. I think that should be all right. Okay, I wasn't able to find a Hamiltonian cycle for this graph either, but regardless, if a graph has a particular has a Hamiltonian cycle, then find Hamiltonian cycle will be able to find it, and you'll be able to highlight it on the graph. I just don't have a particular example of that in this lecture. All right, so this is what I was referring to before. So one of the interesting things that you can do with graph theory is look at certain measures of connectivity. Or how closely certain vertices are connected to each other or to the graph at large. So there are a number of traditional measures used for this. And Wolfram Language has all of these built in. Various measures of centrality based on certain algorithms. So as I said before, we have this resource data, which has information about these families in Florence, Italy, which were very politically and economically connected to each other. And the Medicis are sort of the most famous of these. They are one of the famously powerful and wealthy families of Renaissance Italy. Now, by looking at this graph, it's not entirely obvious why. They only have these 5 connections. These have 4 connections, but who's heard of the Strozzi's? Or the Tornabuoni. So why exactly were the Medicis the most powerful and best known in Renaissance Italy? So we have all these measures of centrality. And so we can take the graph here and we can highlight it based on several different sets of properties. And so if we take this, this network, we can see that by all these different measures of centrality, the Medicis are the center in most of them, not all of them, but by several different measures of centrality, we can see that the Medicis were the best connected. So even if they didn't have the most money or the most political influence, we can see that they were connected, and the connections are what enabled them to become so powerful, and why they are so well known and why they had so much influence. Is they used their connections, and we can see that with all these different measures of centrality, it's clear that the Medicis had access, direct or indirect, to a very large chunk of Florence's political structure. So they were able to call in favors. So beyond measurements of connectivity, we can do some clustering of graphs. So we can see where a graph breaks down into chunks or clusters. We saw with the dolphin social network that there were certain pods that the dolphins mostly align themselves in. And so again, we can use the /dot-data. And so we can look at the number of weakly connected components, and we can sort the elements of the subgraph by how many connected components they have. So like if I have, don't know why that happened. So if I have a graph which has some set of subgraphs, or not necessarily subgraphs, but chunks that are mostly self-connected with a few connections outside, we can see what the largest of these subcomponents are. It's sort of like, you know, on Reddit, if I have all of these various subreddits and there's some crosstalk between each other, people are posting on one and the other, but, you know, some of them mostly stick to themselves and they mostly communicate within themselves, but they sometimes communicate with other outside groups. So we can see what the largest weakly connected component is. Like how big are the biggest subreddits or biggest subgroups of this, not in the group theory sense, just in like a clump of edges and vertices. And so we can take a look at that. And you can compare, again, various measures of how well connected these subgroups are, how connected they are within each other and to the other clusters. Running a little low on time, so I'm just going to sort of go through this last part very quickly. Again, and we can also measure, we can also use graph theory measures to see how well connected various companies are and how that might relate to their performance in the stock market or in other market trends. So this is one that is just built in. And so we can find clicks within, hold on. I don't know why that. I think this was originally evaluated with a different example. Oh, well, regardless. So you can find a group of vertices within a graph that form a clique. Basically an in-group that does not connect with other clusters. And so you can compare like how many connections there are within each of these cliques. And again, you can just visualize that with functions like histogram. All of the built-in ordinary plotting functions are included in the Wolfram language. And we're going to be talking about that more in the next couple lectures when we get started on the visualization component of this course. Now, just to sort of come to the end, I do want to talk about a couple of things which are, some of which are new to Wolfram language version 12.1. Previously, prior to 12.1, graph edges were exclusively defined by their relationship between vertices. So if I have this graph here, which is defined as a red vertex going between 1 and 2 and a blue vertex going between 1 and 2, you will see that in this graph, actually, let me zoom in on that. I'm just going to zoom in on everything. Oh. Well, there we go. So we can see that the two edges going between vertices 1 and 2 are in fact both red, as opposed to one being red and one being blue, as you might hope. This is because the edges themselves in the pre-12.1 graphs are exclusively determined by their relationship to the vertices. There is no independent 1-2 for this edge and 1-2 for the other edge. These edges are both effectively the same edge just because they're going between the same pair of vertices. So in Mathematica 12.0 and before, you can only ever have a single set of properties for any edges between two given vertices. In 12.1, there's now a new function, the function edge tagged graph. And so now finally, you can say, now in edge tagged graph, I specifically want this edge to have this property and this edge to have this property. Actually, I'm going to change that to green just to make it pop from the other two edges. So now you can assign independent properties to edges going between the same vertices in 12.1 plus. You could not do that before, at least in core Wolfram Language. One important thing with Wolfram Language is that there are also a number of user-defined extensions, a wide variety of packages which are intended to extend the functionality of the Wolfram language or, increase its usefulness for a particular application. I understand that many of you are working in scattering experiments. There is a very popular package, FeinCalc, FEYNCALC, which is intended to do Feynman diagram-based calculations. And FineArts, similarly, is designed for Feynman graph visualization. So even if there is not something in the core Wolfram language that works for your particular field, there are often third-party creations that are available that extend that functionality. All right. And so here I just include another example of an edge-tagged graph where the weights are assigned to these different edges. And so you can see that the weight is taken into account. And each of these independent edges now has an independent weight and an independent color. And the flow through this graph is taken into account appropriately. All right. So now we're sort of coming up to the end of the first part of the lecture. And we're basically, the material has been presented. And now I'm just going to say, here are a couple of explorations and exercises. Just a couple of sort of introductory, but also meaty things that, problems that you can sort of sink your teeth into. These are a couple of problems which you can work on. I believe there are groups for this session. And basically, I just have constructed a couple of exercises which I think would be good starting problems. And here are a couple of hints that are included as well. If you double click on this, you can see the hints. Collapse that. Mm-hmm. And so basically, yeah, I have a couple of exercises that that hopefully you can get started on, and we can discuss any questions you might have on those. and you can choose to present these at the end as part of your final presentations. There will also be other slightly more elaborate problems that I'm going to be introducing in the next lecture as well. Here's a question. Do all of the students have the presentation notebook? Did I send that out to everybody?
I don't have it.
Okay.
Is it posted on Slack?
I will put it in the Slack right now. Hold on just one
Slack
moment.
is dead.
Yeah, Slack is down.
Oh, Slack is down? In that case, I will just create a link to we use the Amoeba file sharing service. Just hold on for one moment. I will upload it there, and then I will put a link in the chat that you can all download this notebook from. Just placed a link to the Amoeba file sharing service in the chat, and you should just be able to download the notebook from there. Hopefully you already have Wolfram Mathematica installed. And there at the end of that notebook, so that's the lecture slides and also the problems at the end. And please let me know if you have any questions. I think I will be here for a few more minutes as you get started. So I will be here for any questions. And I will also be here tomorrow, I believe. Is that our next scheduled lecture?
Yes, it is tomorrow.
All right. Okay. All right. And so tomorrow we will be continuing on with some of our explorations, some of the problems. And also tomorrow we are going to get started on the material for our Gen 106 course about data and function visualization in the Wolfram language. All right. Please let me know if there are any questions. So I've just presented a couple of problems here, just sort of abstract, not particularly real world data. Oh,
we have a couple of hands up. Manuel, Perfect. Would you like to go first?
Yes, thanks. First of all, Duncan, thank you very much for the nice lecture. I have a question which is, I would say, related and unrelated at the same time. Could you please go back to your slide 28?
All right. Hold on a second. Yes.
Thanks. So my question is about that kind of graph. So I was playing around with isomorphic graph Q, trying to figure out, because I don't really care usually about what the edges and the nodes are labeled, but I care about the shape of a graph. So everything was fine until I got to a graph of this kind of shape. So where you had two nodes connected by two lines. And there I get, it says something like this generalized graph is not implemented yet. So I was wondering if, because here you were talking about properties assigned to the edges. So I was wondering if there is this kind of graphs have anything special which makes them harder to deal with, or if there is anything I should know before maybe trying myself to extend this feature so that I'm able to take this kind of graphs into account as well.
As far as graph isomorphism goes, I think they should be able to handle multigraphs relatively painlessly. I don't think there should be anything special about multigraphs that should prevent it from working with other algorithms. It's just the properties assigned to the edges themselves that were an issue before 12.1 and edge tagged graphed. So if you could send me an example, I can take a look at that, and if necessary, I can forward it to the graph developers.
Yes, that would be great. Thank you very much.
I just want to say that I've had the exact same type of problem that Manuel is talking about.
It's amazing because me too.
Yeah.
All right.
I've actually had to add an additional vertex to one of the legs.
Yeah.
To be able to use graph isomorphisms at all. But maybe that's fixed now that there's some kind of distinction between the two edges.
Right. That's possible. Yeah, if as soon as Slack is back up, if you could put those examples in there, I would be happy to take a look at those and, if necessary, forward them to the appropriate people.
Thank you very much.
I've also had similar problems, and I've been using a package called iGraphM that was able to do a lot of things that the native functions did not do. If you, maybe you can check that out.
Yeah, so I'm familiar with iGraph. The creator of iGraph, Sabol Shorvat, is one of our longtime power users. He has sent in a truly massive number of reports, suggestions, etc. And he's also a frequent responder on the Mathematica Stack Exchange. He is a valuable member of the Wolfram community. Yeah. But yeah, as I mentioned before, the Wolfram language has a wide variety of extensions that have been created, some by us, some by other users. Hopefully, no matter what you want to do, there's always something that you can use. All right. Okay. Well, I will be here up until 1/2 hour, and then we'll meet again tomorrow. And hopefully I can address any questions, any further questions that you have then. All right. I'm just going to stop sharing for the moment. Okay.
Actually, this is a good opportunity for everyone to unmute themselves just for a moment and give Duncan a round of applause.
Well, thank you very much.